All right, here our goal is to get a slightly better and more deeper understanding of the notion of stresses. And so let's imagine sort of a generic three-dimensional surface that might be shaped like this. You may identify a piece of area over here. Let's call this piece of area dA. And the notation that we will use is the outward normal from the surface at this location will be the direction of this area vector, right? So area is a quantity, we know it's got magnitude in it. It also has an orientation, and that's what we're introducing over here. And the orientation is always defined to be the perpendicular outward normal associated with that area. And let's imagine we have a force acting at this point in this direction. Let's call this force direction force magnitude delta F. Okay, and so delta F, this quantity delta F is a vector quantity, and now I can break this up into two components. I can break up delta F. Let's say the vector looks like this, delta F. I can break it up into two components, one which is parallel to this area vector, and the other one which is perpendicular to this area vector. And let's complete this parallelogram or rectangle, if you will. All right, so this one is going to be the component of F that is tangential to the surface, and this is the component of F that's normal to the surface. All right, so delta Fn and delta Ft are the normal and tangential components of this force. So I can define the normal stress sigma n as delta Fn divided by delta A, right? So I can think of this delta A as essentially either the magnitude of the area vector, which I can formally write it as the magnitude of that area vector. And technically this is in the limit as this delta A approaches 0, right? As it becomes very small and it really collapses to a point, that'll be the value of the normal stress locally at that point in space. Same way, the tangential stress, I can think of that as tau. Tangential is going to be delta Ft divided by delta A, which I can leave it as delta A, or I can put a magnitude of the vector in the denominator. I'll leave it this way. And formally, it is a limit as delta A approaches 0. So this will be my tangential shear stress. So this concept comes in useful in trying to understand sort of the definition of a fluid. And let's introduce this following scenario. Let's say you have a bottom plate and you have a top plate, right? So the bottom plate might be fixed and the top plate might be set in motion. Let's say it's moving. So the upper plate moves to the right at some velocity, let's say speed v. Okay, and let's imagine that the region in between these two, this region in between the top plate and the bottom plate, is occupied by a fluid, right? So I got a top plate, I got a bottom plate, and the bottom plate is fixed, the top plate is set in motion in a certain direction at a speed v, and there's fluid in between these two plates, right? Now if I sort of take the edge view, so I have the top plate, I have the bottom plate, and let's imagine we mark fluids by coloring it with a dye. Let's imagine we mark a line of fluid which is colored by a dye. Okay. Now, once the top plate is set in motion, there's a tangential stress tau that's appearing on the top surface of the fluid. And what's going to happen after a short time later is this marked fluid, this dye, is now going to look like this. It's going to move to the right. And as the tau continues to be present, at a later time, it's going to take that position. And at a still later time, it's going to take this position. So this is what I mean when in the definition of a fluid, this quantity tau, the shear stress, can be very small, however small, Nevertheless, it's going to set the fluid in motion. And this is the picture at early time. And this is the picture at later times. And as time increases, the motion continues, right? So imagine marking this fluid by a dye, and then all I'm looking at is a trace of this dye at later times. So hopefully this kind of gives you a better sense of the definition of a fluid and how the notion of tangential stress